More of everyone's favorite ideal gas law problems. So we're still performing calculations involving temperature T, pressure P, volume V, number of moles of gases, and of course we always know for ideal gas law the R is 0.0821 liter atmospheres per Kelvin mole. That's a given. Okay, so the question right now is determine the temperature in degrees Celsius for a sample of neon with an initial volume of 2.5 liters at 15 degrees Celsius when the volume is changed to 5.0 liters and pressure is constant. Okay, so we know the equation is PV equals nRT, but if we're really looking at this, pressure is constant means that the pressure is not changing. We're told that there's an initial volume and a second volume, so we know that this really isn't the correct form of this equation. What we have been given is a V1 and a V2. We are trying to find some temperature at some final point, so a T2, and this initial volume is at a initial temperature. So we need an equation that relates V's and T's, and we can derive that from PV equals nRT. So we remember, so looking at this, there's two ways to do it. First up, we can look at these two are on opposite sides, and we know that the rule is opposite sides divide. So if we remember the rule opposite sides divide, first way we can do this, which is the fastest way, is we'll end up with V1 over T1 equals V2 over T2. And that's one of the rules that was used to derive the PV equals nRT, so we know that this is correct. V and T are on opposite sides divide. So where did that opposite sides divide come from? Well, in order to solve this, where pressure is constant, but we've got two variables, V and T, we'll put the variables on one side and we'll put the constants on the other side. So we're going to rearrange this equation using algebra. So our constants are P, N, and R. R is always a constant. In most of these questions, N's a constant. It's literally telling us P is a constant. Okay, so we want our V and T on one side, P, N, and R on the other. So I'm going to start by dividing both sides by T. That's going to eliminate it from this side. And we have PV over T equals NR. This is a great start, but we know that P is a constant. We need to get that P over to the other side. So we're going to do that by dividing by P. 1 over P. That's going to cancel. V over T equals NR over P. Okay, so the trick here is this is constant. This doesn't change between the initial and the final. So we know that if we did the exact same thing for the final, we get V2 over T2 equals NR over P. And so in this particular equation, we know that if A equals B, V1 over T1 equals NR over P, and B equals C, because NR over P, that's our B from the initial, or equals V2 over T2. This is different. This is a 2. It's different than 1. It's a new condition. Therefore, if A equals B and B equals C, A must equal C. So we will know that V1 over T1 equals V2 over T2 because we were able to set them both equal to the exact same thing. That means they are equal to each other. So we've derived that two different ways. So this is the long way to do it, or you can remember opposite sides. This is on this side, this is on the other side of the equal sign. Opposite sides divide. It's V1 over T1 equals V2 over T2. So that's the first tricky thing, deriving the equation. Second tricky thing, it calls for this in degrees Celsius, but we know any time we're using PV equals nRT, temperature has to be in Kelvin, otherwise it doesn't work. It has to be. So the first thing we're going to do is we're going to take that 15 degrees Celsius, We're going to add our 273 Kelvin to it. Let me pull out my calculator. 15 plus 273 equals 288 Kelvin. 288 Kelvin. So we're not going to use that. We're going to use 288 Kelvin. Okay, so now we know our equation is V1 over T1 equals V2 over T2. We're solving for determine the temperature, the final temperature in a sample of neon with initial volume of 2.5 at that. So this is T1. And when the volume changes to 5.0 liters, and that's V2. So we're solving for T2 right here. So what I'm going to do first is multiply both sides by T2 and get T2 on its own. That's going to cancel. T2 times V1 over T1 equals V2. Okay, and then I'm going to multiply both sides by T1 over V1, the reciprocal of this. So T1 cancels T1, V1 cancels V1. And do the same thing on this side. T1 over V1. So now we have our equation. T2 equals V2 T1 over V1. And now we just plug in and chug. Our V2 is 5.0 liters. Our T1 is it's not 15 degrees Celsius, it's 288 Kelvin. And then our V1 is initial volume of 2.5 liters. 2.5 liters. Boom, boom. Okay, so doing that calculation, we're going to plug in 5 times 288 divided by 2.5. That gives us a value of 576. 576 Kelvin, but they want this in Celsius. So I'm going to pause here and clean up, and then we're going to convert that back to Celsius. See if you can do that on your own. Okay. So just delete a little bit over there. So we've gotten from the math 576 Kelvin equals what in Celsius? So all we're going to do, we had to add to get Kelvin, so we're going to subtract it back out. 576 minus 273 equals, oops, dropped my calculator for a second there. 576 minus 273, 303. 303 degrees Celsius. And that is our answer.